Electronegativity, attracting electrons. So, when two atoms form a bond, each atom attracts the other atom's electrons in addition to its own. So the electronegativity of an atom is the measure of an atom's ability to attract the electrons, okay, that are formed in a chemical bond. So we're going to use the symbol En to show electronegativity. So electronegativity is the periodic property of atoms that are involved in chemical bonds. So En, so the electronegativity, as we move up the group and across the period, increases. Okay, so really very similar to what we've seen in terms of electron affinity and atomic size. So let's look at what we talked about in the previous lesson about some of the other periodic trends and compare it. So we've seen this before. We've seen the following periodic table before when looking at trends in the periodic table. And how do we know the direction in which the electronegativity increases? Well, as we said, if we know what the atomic radius is, okay, and we look at the direction in which it's doing whatever it's doing, if it's increasing or decreasing, remember that, as we said before, the electron affinity and the ionization energy is always the reverse of whatever the atomic size is. So the electronegativity is no different. So the electronegativity, I can't spell it. The electronegativity is also the reverse of the atomic size. So, the trends for electronegativity is the reverse of the trend for atomic size, similar to the ionization energy and electron affinity, just what I showed you a moment ago on the periodic table. So, as the atomic size decreases from left to right, okay, across the period, electronegativity increases. Okay, so what do we have here? Well, atomic size decreases, electronegativity increases. Why? So let's look at why that does. So, because the number of protons in the nucleus increases, right? Because as we said, as we move in this direction on the periodic table, the atomic number increases, which means we are also increasing in the number of protons. So at the same time, the number of filled inner electron energy levels, okay, remains the same. So we keep adding an electron also when we're going. So we're adding protons, we're adding electrons to the atom. And the atom is now being pulled more tightly to the nucleus, resulting in a smaller atomic size. Okay? And in turn, the atom attracts a bonding pair of electrons more strongly because the bonding pair can move closer to the nucleus. Okay. So, ionic versus covalent. You should already know this, but let's recap some of this stuff. Ionic compounds are compounds that are comprised of a metal and a non-metal. Ionic compounds form repeating units. The reason for that is, well, opposite charges attract. So let's look at an example here. A very common one used in chemistry is sodium chloride. So we know if we look at an atom of sodium chloride, we have Na and we have Cl. Okay? And we know that Na is a positive charge, chlorine is a negative charge. So there's an attraction because they are oppositely charged. Okay, there is a charge between them. But now we're going to have another Na and another Cl, right? Why? Because now the Cl, which is negative, is attracted to the positive Na. The Na attracted to the negative Cl. Okay, so and then underneath here, Cl, Na, Cl, Na. Okay, so notice here, whenever we have sodium chloride, they form, it could be millions, okay, like a great amount of atoms that are bonded together to represent sodium chloride. Why? Because there's this attraction of opposite charges. Okay. There is an attraction within the positives and negatives of within ionic compounds. But now, covalent compounds share their electrons. They form distinct molecules. So let's look at a very common molecule, such as H2O. So we're going to have oxygen. Okay, and ball and stick. Actually, I shouldn't have done that. H. And as what we're going to see in a moment, if we look at oxygen is going to have a pair of, two pairs of shared electrons surrounding it, which makes oxygen slightly negative, which in turn makes hydrogen slightly positive. And we're going to see a little bit more about that in a second. Now, when water forms a bond, water is being attached to another molecule of water because of the attraction between the slightly positive hydrogen with the slightly negative oxygen. And this kind of attraction occurs between covalent compounds. And covalent compounds, a distinct molecule. Here's the one molecule. Okay? But here, in terms of NaCl, all this NaCl. So they form a very big unit that can be put together. But here, we're looking at a very distinct molecule in which, to attach other water molecules, there is an attraction, okay, that kind of keeps them together. It gives water that property. It's that property that allows water, if you fill the glass up with water, it allows you to kind of bring it above the brim. Okay? So, let's move on. Intermolecular versus intramolecular forces. Intramolecular forces occur within the atoms of a molecule. So let's go back to that example of water. There is an intermolecular force that is keeping these atoms together. Very strong bond to break. Okay, very strong bond to try to break. And while intermolecular forces are between more than one molecule. So we'll have, as we showed you guys, I'm going to simplify the diagram and just do it this way, where the slightly negative oxygen is going to be bonded to the hydrogen of another water molecule. So there is an attraction between the slightly negative oxygen with the slightly positive hydrogen. And the same thing goes with another oxygen molecule, let's say, of water, where the oxygen is slightly negative, the hydrogen is slightly positive, and there's an attraction here. And so what we have here, what I've demonstrated, are three molecules that are held together by an attraction between the positive and negative ends of the actual atom. While the intramolecular force kind of looks at the actual bond itself and the attraction that occurs between the actual atom with the other atoms that are surrounding the entire molecule. So which bond is strongest? Well, obviously the bond that actually holds the entire molecule together. So, equal versus unequal electron sharing. Ionic compounds have been known to be formed when metals lose their valence electrons and give them up to their non-metal counterpart. As a matter of fact, all bonds share electrons. Okay, despite what we've known that covalent is the only one. However, that sharing is can either be considered equal or an unequal type of sharing. And that's really what we're going to be looking at. So what we have here are three types of bonds that occur: nonpolar, polar covalent, and ionic. And this nonpolar is nonpolar covalent bond. Okay? So what we've looked at before was really separating between ionic and covalent, and now we're going to be looking at two types of covalent bonds, the polar and the nonpolar. So what we're going to look at here is we're going to use the Greek symbol theta. If you can't see it, I'm going to draw it a little bit bigger. Okay. Which means partial charge. Okay. So what we have here, if you can look closely, we're looking at, let's say, an example of two hydrogens put together, right? H2. So the bond and the electrons that are surrounding it come really close together. Okay, so we're looking at maybe the nucleus within here and the electrons pretty much circling around that. Sorry for the diagram, but anyway. And so what we have is a sharing of the electrons. Okay, and in fact, because they are two exactly the same atom bonded together, there is no polarity. So there is nothing that is considered slightly more positive than the other end. So the entire end is considered the same. But let's look at another example here. So an example of a polar covalent compound. We're looking at something like hydrogen, okay, HCl, hydrogen chloride. We put those together. Here, the smaller atom of hydrogen, bigger atom of chlorine, bonded together to form a polar covalent bond. Okay, what happens here pretty much is, well, we have all these extra electrons that are circling around the chlorine, right? Because chlorine has 7 valence electrons plus the one that it's sharing with hydrogen, 8, while hydrogen has the one of its own and the one Cl that it's sharing. And so what we have here is a slightly negative end and a slightly positive end, resulting in what we call polarity. So we know that we have a part that is slightly positive and a part that is considered slightly negative. But ionic, on the other hand, let's say we have something like lithium chloride. So we have lithium here, and we know lithium has a 1 valence electron, which it's going to lose it, okay, to chlorine. Let me just draw these a little. Okay, and which has 7 valence electrons. So it picks up the 1, so which by losing that electron, it becomes slightly positive. Chlorine becomes slightly negative, and there is an attraction because they're oppositely charged, but the attraction, the gap between the two atoms is not quite the same as the gap between the polar covalent bonds. Okay? So, because of this, we don't have a slightly positive, slightly negative. We actually, in fact, have a positive end. We, in fact, have a negative end. So, we can use electronegativity value to identify whether what the nature of the bond is, if it's ionic, polar covalent, or nonpolar covalent, using the electronegativity numbers that we have on our periodic table. Okay, and we do this by finding what we call the electronegativity difference. So, which is shown by this, the change in electronegativity. So what you're going to do is you're going to take the electronegativity of one of the atoms and subtract it by the electronegativity of the other. So if you had something like lithium chloride, as we were looking at lithium and chlorine there, you would take the two values. Okay, so chlorine is 3.0, lithium is 1.0, and the result is a change in the electronegativity with lithium chloride, as we looked at in the previous slide, and we get a number of 2.0. But what does that mean? Well, let's look at the following chart. So here's the chart. So we're going from the number from 0 all the way to 3.3. So if that number, as we just calculated, right? So lithium chloride, we got a number of 2.0 for our change in our electronegativity. So that value is within here. So it's considered mostly ionic, just as we saw. Lithium became completely positive, chlorine became completely negative as it picked up that electron. Now, if we had a value that is between 0.5 and 1.7, it is considered polar covalent, which would, if we look at the electronegativity number and you take the higher value, higher electronegativity value, that is the atom that is going to be slightly negative. And the number with the lower electronegativity number will be considered slightly positive. And then if you have a value that is between 0 and 0.5, it is completely non-polar covalent, which means there will be slightly no, there will be no partial charge. Okay, so they're pretty much not going to have the positive negative ends. And this is very similar with water, because we know water is polar covalent. And we know, what does it mix with water? Oil. Why? Because oil is a non-polar covalent compound, while water is polar covalent. And that's one of the reasons why water and oil don't mix, because oil doesn't have the positive negative ends that it needs to allow it to mix with oil. So let's try to find the change in the electronegativity of the following three examples. And if you take the values and take a moment and find the electronegativity number of hydrogen, and obviously because we're looking at hydrogen and hydrogen, we know that if whatever the values happen to be, we will subtract them and we will get an answer of 0. So if we look at the number, we're going to get 2.1 minus 2.1, which will give us a value of 0. So hydrogen gas is at 0, which means it is considered non-polar covalent. Okay, so oxygen and water, we know that oxygen. So what you do here, because we have more than one H, what we're looking at is you take one of them and you take the other. And what you're trying to find is there, what's the change in electronegativity within that bond. And then you're going to look at what is the electronegativity of between that bond. And it's not going to really matter because they're both the same. So you just find one of the values. So we look up oxygen, and oxygen has a value of 3.5. We're going to subtract it by the electronegativity of hydrogen, which is 2.1. And we get a value of 1.4. So 1.4 within the polar covalent. Okay, polar covalent, which means the higher of the two electronegativity numbers means that the oxygen is slightly negative, while the lower the value is slightly positive. And let's look at the last example here. We have methane, which is CH4. And again, we're looking and we're comparing between one atom and the other. So we're looking at comparing between one bond and the other, and we get 2.5 for carbon. We're going to subtract it by the 2.1 electronegativity, and we're going to get a value of 0.4, which lies within this non-polar covalent range, which means that CH4 is non-polar covalent, which means none of the ends are slightly more positive, slightly more negative, which means one of the reasons why this wouldn't mix with something like water. Okay, why a non-polar covalent, and if a molecule was non-polar covalent, it will not mix with anything that is considered polar covalent.